Okay, we are in section 2.5. 2.5, rational functions. Rational functions, okay? Well, they talk about rational functions, and a rational function is any function in the form f of x equals p of x over q of x. And I gotta be careful, I can never allow for division by zero, so I'm gonna require that q is never zero, okay? And this is where p of x and q of x are polynomials, okay? So a rational function is any function of the form f of x equals p of x over q of x, where p of x and q of x are polynomials, okay? So a couple of examples. We'll write the function, then we'll write the factored form. We'll see what that means. And then we'll write the domain. Okay, so the simplest rational function is f of x equals 1 over x. That's the simplest rational function. And it's already in a factored form. So I don't have to do anything to him to make sure that he's already factored. It's a very basic function, and it is already in its factored form. And the only thing I have to worry about in terms of the domain, okay, the domain is the x value that I allow into this function. So the domain is going to be all reals, set of all x, such that x is not 0. So I got to stay away from 0 because I can never allow for division by 0. Well, this set is the same thing as a set from negative infinity to 0, union 0 to infinity. So I can write that domain either in interval form or in what we call set builder notation. Right? There's interval notation, there's set builder notation. The second example of a rational function they give me is g of x equals, they say 5x squared divided by 2x squared plus 5x minus 12. Okay? And the factored form, they're just asking me to make sure that my numerator and my denominator are factored. I can factor this polynomial in the bottom, 2x and an x. Okay? To get a 12, you can do a 3 or a 4, or 2 and a 6. We're going to do a 3 and a 4. A 3 and a 4. And I need a positive 5x, so I'm going to put a plus with the 4 and a minus with the 3. So 2x minus 3 times x plus 4 will give me 2x squared plus 5x minus 12. That's why they call this the factored form. I took my denominator and I factored completely. And you could FOIL out this binomial times that binomial and you'll get that trinomial. 2x times x gives you the 2x squared. 2x times 4 is a positive 8x. That's the outer product. The inner product is the negative 3x. So positive 8x minus 3x gives you a positive 5x. So you get the middle term here from the combination of the outer and inner product. Then negative 3 times 4 gives me a negative 12. Okay? The domain of this thing, and that's why we need this fully factored form. We're going to need the fully factored form before we can properly determine the domain. The domain, again, I just have to stay away from everything that makes my denominator 0. Well, this factor is pretty easy. Negative 4 plus 4 makes 0. So my domain would be the set of all x such that x is not 4, right? Negative 4. So I got to stay away from negative 4. And I got to make sure that I never allow this to be 0. So you might have to do a little bit of arithmetic here. Where can 2x minus 3 be 0? Well, I add 3 to both sides. 2x equals 3. X equals 3 halves. So x can't be 3 halves too. So there's my domain. The set of all x, all real numbers x, except where x is negative 4 and where x is 3 halves. That'll be my domain, okay? And if I want to write this in interval notation, negative infinity to negative 4, union, negative 4 to 3 halves, union, 3 halves to infinity. That would be the domain for that function, okay? All right, in interval form, all right? The third example they give me is k of x equals, they give me x plus 3 divided by x squared plus 4. And the fully factored form for k of x, I can't do anything about that x plus 3. The question is, can you factor x squared plus 4? And the answer is no. You can factor the difference of squares. This is a perfect square, x squared. 4 is a perfect square. If I had x squared minus 4, I could factor it. But x squared plus 4 will not factor. Try all you want, it's already factored. So even though they look like they might be factorable, sometimes they aren't. You cannot factor the sum of squares. Try it if you want. And whatever combinations you get, if you FOIL it out, you will not get x squared plus 4 back. So since this thing, I couldn't factor it, and think about what you're doing. Whatever x is, you're going to square x first, then add 4 to it. So this thing will never be 0. Again, whatever x you put into this function, you're going to square that x, then add 4. So the denominator will never be 0. So the domain for these rational functions was always everything except what made your denominator 0. So my domain would be all real numbers. X such that x is a real number. It's all real numbers, it's everything. The way I write that in interval form is negative infinity to infinity. So the domain of him is everything. So these are rational functions. Again, the numerator is a polynomial, the denominator is a polynomial, okay? And you can even talk about the degree. This is a polynomial of degree 2. This one is a polynomial of degree 2. The highest exponent on the variable determines the degree. This one is degree 1, x to the first plus 3. The bottom here has degree 2. 1 has degree 0. Any whole number, any number rather, whether it's 1 or 1/2 or 3/4 or negative 6, a number will have degree 0. Okay? A number will have degree 0. And that kind of makes sense. If I said that 2x squared has degree equal 2, and x plus 1 has degree equals 1, because there's x to the first. Well, when I write a number, it's like 2. Technically, what I can write is 2x to the 0. X to the 0 is 1. So whenever you write a number, you can think of that number times x to the 0. And again, since the exponent determined the degree, x to the first, degree 0, x to the 0 means this is degree equals 0. So numbers, negative 8, will have degree equals 0. All numbers have degree 0 because a number is just that number times x to the 0. Okay? So numbers always have degree 0. So these are rational functions. Pretty easy to determine their domains. And we're going to analyze these rational functions. We're going to graph them, and we're going to learn about them in this section. Okay? All right. Well, let's go ahead and graph. Let's go ahead and graph that most basic one. F of x equals 1 over x. Well, if you want to graph a function, you can graph any function that exists with the t-chart. Choose values of x, plug it into the function, and get corresponding values of y. Okay? Now again, I know the domain of this function though. The domain of him, we just wrote it down, is all real numbers except 0. So I can't choose 0. But I can choose 1, I can choose 2, I can choose 3, maybe negative 1, negative 2, negative 3. If I put a 1 in here, f of 1 would be 1 over 1 over 1. So when x is 1, y is 1. If I put a 2 in here, everywhere I had an x, I put a 2. That's 1/2. Put a 3 in here. That'll be 1 over 3, or 1/3. Put a negative 1 in here. That's 1 over negative 1, that's negative 1. Put a negative 2 in here, you get a negative 1/2. Put a negative 3, you get a negative 1/3. So pretty easy to evaluate the function at a given point. So let's see what the actual graph looks like X and Y, 1, 2, 3, 1, 2, 3, 3, 1, 2, 3. Okay. The point 1, 1 would be right here. 2, 1/2, I go over 2 and up 1/2 right here. 3, 1/3, 4, 1/4. The pattern continues, so the function does this. Okay. Let's do these. -1, -1 would be right here. -2, -1/2. Start at the origin. I go x equals -2. Y is -1/2. About right there. -3, -1/3. I go origin, -3, -1/3. About right there. So now I see the function doing this. Okay? So far that's what I've got with the points that I've plotted. Well, again, I know x can't be 0. X can't be 0. Okay? Because that's not in my domain. 1 over 0 would be division by 0. I can never allow that. So x can't be 0. X equals 0 is the entire y-axis. Note, x equals 0 is the y-axis. Every point on the y-axis has an x-coordinate of 0. If I look at this point right here, this is the point 0, -3. The point right here on the y-axis, this is the point 0, x is 0, y is 1. That point right there on the y-axis, x is 0, y is 3. So every point on the y-axis has an x-coordinate of 0. So this graph will never touch the y-axis. This graph will never touch the y-axis. So the question becomes, though, since it won't touch the y-axis, I don't know what it's doing between 0 and 1, though. And I don't know what it's doing between 0 and -1. Anytime you don't know what a function is doing in the interval, that just means you need more points in that interval. So let's continue our t-chart thing. I'll move it over a little bit. Let's continue our t-chart. Do it down here. And I got to get points in this interval between 0 and 1. So let's say x equals 1/2 or x equals 1/3. And do some negatives. Let's do -1/2, -1/3, etc. Plug those numbers into my original function. So f of 1/2, the function, whatever you put in it, is 1 over that thing. So 1 over 1/2. You can take your calculator and do that if you want, but when you're dividing by a fraction, keep, change, flip. Keep the 1 in the top, the 1. Division changes, that's the change. Keep the 1, change division to multiplication. Flip the 1 in the bottom. That gives you 2. So when x is 1/2, y is 2. Now do 1/3. F of 1/3 would be 1 over 1/3. Keep, change, flip. Keep the 1, change division to multiplication. Flip 1 over 3 becomes 3 over 1. 1 times 3 over 1 is 3. Do -1/2. 1 over -1/2. Keep, change, flip. 1 times -2 over 1. That's -2. By the same token, you'll get a -3 there. So plot those points. So there's 1/2. Go over 1/2 and go up 2. 1/3, 3. Go over 1/3 and then it'll go up 3. So now it becomes clear. That graph will do that. Do this one, -1/2, -2. So go over -1/2, down -2. -1/3, -3. So now we see clearly that the graph does that. There's the graph of y equals 1 over x, or f of x equals 1 over x. So we notice again, that graph did not touch the y-axis. That graph did not touch the y-axis. The y-axis is a vertical asymptote for this function. We're going to talk about asymptotes in a minute. I'll go ahead and write this. The y-axis is a vertical asymptote for the function. A vertical asymptote. It's just a vertical line, an imaginary vertical line that the function will never cross. That's all a vertical asymptote is. An imaginary line, vertical line, that the function will never cross. So this function has a vertical asymptote at on the y-axis, which is really x equals 0. That would be the equation of it. Vertical lines have equations x equals some number. Horizontal lines have equations y equals some numbers, if you remember. So the y-axis, the equation for the y-axis is x equals 0, and that y-axis forms what we call a vertical asymptote for this function. This function will never cross the y-axis, okay? And we can kind of analyze the behavior of this function. And we're gonna write it this way. I'm gonna say as x goes to, we're gonna go to that asymptote. So as x goes to 0, because again, we said the equation for the asymptote was x equals 0. The y-axis has equation x equals 0. And I want to talk about what the function does as I go to 0 from bigger numbers, from the positive side. I can come to 0 from these numbers, from 3, 2, 1. I'm coming to 0, what is my function doing? Or I can come from the negative side of 0, negative 2, negative 3, negative 2, negative 1. I can come to 0 from that way. So the way I write it mathematically is, as x goes to 0 from the positive side, that means I'm coming this way. X is 3, the function is here. X is 2, the function is here. X equals 1, the function is here. X equals 1/2, the function is there. X equals 1/3, the function is there. So clearly as x goes to 0 from the positive side, my function is going to infinity. If I did x equals 1/10, right? If I had 1/10 here, the function would already be at 10. And if this were 1 over 100, the function would be at 100. So as I get really close to 0 from the positive side, that's what that means, the function blows up and goes to infinity. Okay? I can also talk about as x goes to that asymptote, 0, this time from, the negative side. So now I'm on the negative side of 0. I'm coming, my function is coming this way. So x equals -3, my function is here. X equals -2, my function is here. X equals -1, my function value is here. X equals 1/2, my function was at -2. At x equals -1/3, my function was at -3. So as I come to 0 from the negative side, my function is now going to negative infinity. So I want to be able to analyze the behavior of the function as I come to that asymptote from either side, from positive side, from numbers that are bigger than that value, x equals 0, or from the negative side, from numbers that are smaller than 0. What is the function doing? As I come to 0 from the negative side, my function goes to negative infinity. As I come to 0 from the positive side, my function goes to positive infinity. That's what that means, and that's what we want to be able to analyze. And I can also say, as x goes to infinity, what does my function do? Right? And as x goes to negative infinity, I want to be able to ask myself, what does my function do? So now, as my function is going to, as x's are getting big, 2, 3, 10, 15, my function is coming down. There's y equals 1. There's y equals 0. So this function is getting closer and closer to y equals 0. So as x goes to infinity, this function is going to 0, y equals 0. As x goes to negative infinity, this one, my function was starting at these negative values, but it's getting closer and closer. So y equals -3, y equals -2, y equals -1, it's going to y equals 0 still. So there's the behavior of my function. And I want to analyze that behavior as that function goes to positive or negative infinity, those last two examples, or as I approach my asymptote from either the left or the right. As I approach my asymptote from the positive side, what does my function do? As I approach my asymptote from the negative side, what is my function doing? Okay? So this is the type of behavior that this function has. Now, we said we had a vertical asymptote at x equals 0. Well, also, look at the x-axis. This function will get closer and closer to the x-axis, never touch it as I go to negative infinity. As I go to positive infinity, this function gets closer and closer to the x-axis, never touches it. So, also, the x-axis, the equation of the x-axis is y equals 0. This is a horizontal asymptote. Okay, so we can have vertical or horizontal asymptotes. This function just happens to have both. A function can have one or more vertical asymptotes. A function will never have more than one horizontal asymptote, but it can have more than one vertical asymptote. We'll see that in a moment. So this function has a vertical asymptote at x equals 0 this function has a horizontal asymptote at y equals 0. This is an example of a function that has both a vertical and a horizontal asymptote. Now I said a function will never cross a vertical asymptote. A function will never cross a vertical asymptote. It turns out that a function may cross a horizontal asymptote. That may happen. We'll see that as we go forward. Okay? So if I were you, I would know this function, f of x equals 1 over x. I'd graph it. I'd be familiar with the graph. When I saw that graph, I said, oh yeah, that's y equals 1 over x. And I would be aware of this behavior, okay? I'd be aware of this behavior. I want to know what the behavior of the function is as I approach positive or negative infinity, okay? All right, I would know this function though, and it will help me a lot in terms of understanding these rational functions, okay? So, example 1. Example 1. The graph of f of x equals 1 over x squared is given. So they give us the graph of y equals 1 over x squared. So there's my x-axis, my y-axis. And I'm not going to draw all this stuff, but y equals 1 over x squared does this. And imagine this thing is all nice and symmetric. Okay? There's y equals 1 over x squared. There's my x-axis, my y-axis. It has this piece, it has that piece. Okay? And they want me to analyze this function. So they say, hey, they say as x tends to negative infinity, as x goes to negative infinity, they want to know where does the function go. B asks, as x goes to 0 from the negative side, as x goes to 0 from the negative side, they want to know where the function goes. C asks, as x goes from 0 to the positive side, they want to know where does the function go. D says, as x goes to infinity, they want to know where the function goes. Okay? We want to answer those 4 questions. Okay, we want to answer those 4 questions. So as x goes to negative infinity, that means we're going this way, negative 1, negative 2, negative 3. The functions, x's are going this way. What is the function doing? The function started off at infinity and is coming down. So negative 1, you're 1, y equals 1. At negative 2, you'd be here. At x equals negative 3, you're here. So the further I get out, the closer this thing is getting to the x-axis, but the x-axis is 0, y equals 0. So the function is going to 0. Y equals 0 is the entire y-axis. Again, there's y equals 1, there's y equals 0, there's y equals negative 1, there's y equals negative 2. That's 0. This function is getting closer and closer to 0 as x tends to negative infinity. Now, as x goes to 0 from the negative side. So 0, right? The y-axis is a vertical asymptote. So as x goes to 0, I'm coming to 0. X equals 0 is right here. But I'm coming from the negative side. So I'm coming from negative numbers to 0. What is the function doing? Well, as I get closer to 0, my function just goes up and up and up and up. It's going to infinity. So the function goes to infinity as I come to 0 from this side. The closer I get to 0, the bigger that function is. Third, as x goes to 0 from the positive side. So now, I'm over here. I'm coming to 0 from bigger numbers. So at x equals 3, the function is here. As x equals 2, the function is here. X equals 1, the function is here. X equals 1/2, the function is up here. At x equals 1/10, the function is always up here. So as I come to 0 from this side, the function goes to infinity. And finally, as x goes to infinity, so now x is getting really, really big, well, my function is getting really, really closer and closer to the x-axis, but the x-axis is y equals 0. So those 4 statements give me the behavior of this function as I approach my vertical asymptote and as I approach either positive infinity or negative infinity. Now I know the behavior of the function. Okay? So that's what we want to be able to analyze. for these rational expressions. I want to know the behavior of what are the y values doing? F of x, what are the y values? F of x is nothing but y. So when I say as x goes to negative infinity, they're saying y is going to what? As x goes to 0 from smaller numbers, from negative numbers, y is going to what? F of x is y, remember that. Okay? Identify vertical asymptotes. Identify vertical asymptotes is what we want to talk about next. Identify vertical asymptotes. Well, vertical asymptotes will occur one in 4 ways, okay? And this function right here, it had a vertical asymptote at x equals 0. So x equals 0 was a vertical asymptote. And it had another horizontal asymptote that was the x-axis. So y equals 0 is a horizontal asymptote. Again, you do not have to have both. Some functions have both. We've seen a couple of examples. But for this function right here, x equals 0, the y-axis is a vertical asymptote. Y equals 0, the x-axis is a horizontal asymptote. Okay? So we're identifying vertical asymptotes. Well, they can occur one in 4 ways. So if you got your x and y axis, you can have a vertical asymptote. The function can approach the vertical asymptote and go up to infinity. The function just gets close to my vertical asymptote, the function goes to infinity. Okay? I could have, secondly, my second scenario, x and y axis, I could have some vertical asymptote, and the function values could go to negative infinity as I approach that vertical asymptote. And in both of these cases, I'm approaching this vertical asymptote from negative side. Okay, so this is x equals a. I'm approaching from the negative side, it goes to infinity. Here I'm approaching a from the negative side, but it's going to negative infinity. So the function is going to positive infinity as I approach from the negative side here. The function is going to negative infinity as I approach from the negative side there. The third way, x, y. I could have the same thing, a vertical asymptote. And as I approach from now the positive side, the function could go to positive infinity. Or as I approach the vertical axis from the positive side, the function could go to negative infinity. But again, in both cases, I'm approaching from the negative side. I'm approaching a from the negative side. So x is going to a from the negative side. Here, x is going to a from the negative side. Here, x is going to, this is a, x is going to a from the positive side. Now, the function is going to positive infinity. X is going to a from the positive side. I'm coming to a from that side. So these are the 4 ways that a vertical axis can arise, a vertical asymptote, I'm sorry. These are the 4 ways that a vertical asymptote can arise. Now, how can we find them though? How do we actually find vertical asymptotes? Well, they say to find vertical asymptotes. Okay. Number 1, we got to make sure f of x equals p of x over q of x. I got to make sure they have no common factors. Okay? I've got to factor those things and make sure they have no common factors. Okay? If they don't, then x equals the zeros of q of x are the vertical asymptotes. Okay? The zeros of that denominator, that function in the bottom, that would be my vertical asymptotes. So example 2, identify vertical asymptotes. Identify vertical asymptotes. So A says the function is f of x equals 2 of x minus 3. F of x equals 2 of x minus 3. Okay. we can see that still. My pen's starting to give out a little bit. I'll replace it in a little while. So f of x equals p of x over q of x. Well, obviously the numerator and denominator don't have any common factors. And all you got to do is ask yourself, what makes my denominator 0? Well, 3 minus 3 would make a 0 at the bottom. So x equals 3 is my vertical asymptote for that function. B, they give me the function g of x equals, they say x minus 4 over 3x squared plus 5x minus 2. Okay, 3x squared plus 5x minus 2. Okay. And take a look at these graphs in the book. I'm not going to try to draw them, but please take a look at these graphs in the book. You'll see a vertical asymptote at x equals 3. Okay. Well, I've got to make sure that the p of x and q of x have no common factors. So I've got to factor first. So I need to factor that denominator. Okay, I need to factor that denominator. That's got to be a 3x and an x. The only way to get a 2 is a 2 and a 1. Okay. I need a plus 5, so that'll be positive, that'll be negative. So there's my fully factored form. Okay. And you could FOIL this out. This times this, and you'll get this thing back. 3x squared plus 5x minus 2. Now, once I factored, I can see that my numerator and denominators don't have any common factors. So my vertical asymptotes will be the numbers that make these factors 0. So if you need to, that 3x minus 1 equals 0. That means that 3x equals 1, or x equals 1/3. So x equals 1/3 is one of the two vertical asymptotes. This one is easy. Negative 2 plus 2 would make 0. So x equals negative 2 is my second vertical asymptote. Okay. So this function would have two vertical asymptotes. You could have one vertical asymptote, two vertical asymptotes, 3 or more, or you could have no vertical asymptotes. C says k of x equals, they give me 4x squared over x squared plus 4. 4x squared over x squared plus 4. Okay? Well, this one they're trying to trick us. Again, x squared plus 4 can't be factored. And it has no real zeros, right? If you try to take x squared plus 4 and set it equal to 0, think about what you're doing. You're saying x. You're going to square the x first, then add 4. Whenever you square something, it's no longer negative. So something positive plus 4, can that be 0? And the answer is no. That'll never be 0. So since there are no, this thing I don't have any common factors in the top and the bottom. And since nothing makes that denominator 0, there are no vertical asymptotes here. Okay? So that function would not have any vertical asymptotes. And the graph of this thing, I'll just draw you a rough, but again, look in the book at these things. That's what this thing looks like. Okay? The graph of this one, and again, look at these in your thing. So 1/3 is 1, negative 2. So negative 2 was an asymptote, 1/3 was an asymptote. This function did this. You had a piece in here that did this. You had two pieces down here that did this. And again, these things can do weird things. So take a look at these graphs. I'm not going to do all of them. So those are vertical asymptotes. Those are vertical asymptotes. I want to do one more of those. I want to do one more of these vertical asymptotes. So that was A, B, C. I'm going to call it D. D, I'm going to say K of X. I'll use K. So I'm going to say P of X equals 2x squared plus 5x plus 3 divided by, we're going to say x plus 1. I want to know my vertical asymptote. So again, factor completely. Can't do anything at the bottom. That is a 2x and an x, no way around it. I need a 3 and a 2, a plus and a plus. Is that right? X squared, 3x, no, that's not right. I need a 3 and a 1, that's what works. A 3 and a 1. So there's my factored form, okay? And when I see my fully factored form, that thing and that thing cancels. That's what they said, that's what they meant when they said make sure your numerator and denominator don't have any common factors. Once I factored, I saw that they had a common factor of x plus 1. So this thing actually is just 2x plus 3. So it looked like I had a vertical asymptote at x equals -1, but since I divide out common factors first and I get this thing, this is just a straight line. I don't have a vertical asymptote at x equals -1. Now, again, the domain of this function is still all x except -1, because -1 plus 1 would make a 0 in the bottom. I can't allow that, okay? So the domain of him is all real numbers except -1, but this thing is actually equivalent to y equals 2x plus 3. Well, let's think about that. That's a pretty easy thing to graph. X and y, 1, 2, 3, 4, 5, 0. So y equals mx plus b. So the b is 3, so I can plot my y-intercept. The slope is 2 over 1, right? So I go up 2 over 1, back on the line. So there's my graph of that straight line. But again, remember, x couldn't be -1. So at -1, I've got to have a hole in the graph at x equals -1. It's a straight line, but it's missing that single point when x equals -1. Okay, that's +1, that's +2. There's -2. At -1, there's a hole in the function. Now, it does not have a vertical asymptote because those common factors divide it out. But I will have a hole in that function. So be careful with these vertical asymptotes. Some functions that look like they have a vertical asymptote don't. Okay? Even that one over there, that one looked like it had vertical asymptotes, it did not. This one looks like it has a vertical asymptote at x equals -1. It does not, it has a hole in the function at x equals -1. Those are vertical asymptotes. Okay. All right. Well, next thing we want to look at is horizontal asymptotes. Okay, horizontal asymptotes. Now, I don't know how good this is going to work. Horizontal asymptotes, again, they can arise one of 4 ways, and we've kind of seen it's going to be the analogy of those vertical asymptotes. I can approach a horizontal asymptote by either from the top, okay? If I've got a horizontal asymptote, the function could come down like that and approach it from that side. It could approach it like that. And if I had a horizontal asymptote, it could approach it either from negative numbers going to it or from positive numbers going to it. If the asymptote, it should be a dashed line, by the way. So one of 4 ways. You can approach it from the positive side, from the negative side, from the negative side, from the positive side. Okay? Now, how you find horizontal asymptotes, there's actually page 303 is where I'm going to refer you. Page 303 is the procedure. I'm not going to write it because it's very wordy. And I don't think this will work very well if I try to do this. Okay, that's not so bad. So if you take a look at that box, we've got a P of X over Q of X. I'm not going to keep holding it up, but basically, when I look at this function, an xn plus an minus 1, xn minus 1 plus a0, that's the P of X over the Q of X, a m, x to the m plus a m minus 1, got a0, and let's call these b's, b, m, b. Call the top coefficients are A's, the bottom B's. So AN, XN, this is an N, these are M's. N is in the top, M is in the bottom. So number one, whenever I have a polynomial like that, or irrational function like that, P of X over Q of X, degree of P of X is N, the degree of Q of X is M. The highest exponent in the top is N. That means that the degree of that polynomial is N. Highest exponent in the bottom is M. That means the degree of the polynomial in the bottom is M. Okay? And those rules said if N is bigger than M, okay? If N is greater than M, F has no horizontal asymptote. Has no horizontal asymptote. So whenever the degree in the top is bigger than the degree in the bottom, there is no horizontal asymptote. Rule number two, if N is less than M, if the degree of the numerator is smaller than the degree of the denominator, y equals 0 is the horizontal asymptote. Whenever the degree in the top is smaller than the degree in the bottom, the line y equals 0 will be my horizontal asymptote. And finally, number three, if N equals M, if the degree in the top is equal to the degree in the bottom, y equals the ratio of those leading coefficients. Y equals AN over BM is the horizontal asymptote. So those are my rules for horizontal asymptotes. Now again, I don't mind if you refer to that page when you're trying to determine what these horizontal asymptotes are. I have no problem with you referring to that page, page 303, and looking at those procedures. I just want you to be able to use it if you were given those procedures. If N is greater than M, we have a rational function. The degree in the top is N as in Noah. The degree in the bottom is M as in Mike, okay? If N is greater than M, F has no horizontal asymptotes. Whenever the degree in the top is bigger than the degree in the bottom, there aren't any. If N is less than M, y equals 0 is my horizontal asymptote. And finally, if N equals M, then the ratio of those leading coefficients, y equals AN over BM, will be the horizontal asymptote, okay? So with that in mind, let's see if we can figure out some of these horizontal asymptotes, okay? So, we're at example 3. Identify horizontal asymptotes. Identify horizontal asymptotes. Okay? Identify horizontal asymptotes. If any, they don't have to exist. Just like with vertical asymptotes, a function may or may not have a horizontal asymptote. Now, it can have at most one horizontal asymptote. There can be more than one vertical asymptote, but can have at most one horizontal asymptote. So A, f of x equals. They give us 8x squared plus 1 divided by x to the 4th plus 1. Okay? Well, the degree in the top is 2. So n is 2. My degree in the bottom, m, is 4. So the degree in the top is smaller than the degree in the bottom. So whenever the degree in the top is smaller than the degree in the bottom, y equals 0 is my horizontal asymptote. So that function has a horizontal asymptote at y equals 0. Again, take a look at these graphs. If that's x and that's y, this function does this. Okay? Take a look at that function in the book on page 304. Horizontal asymptote at y equals 0. B. Part B says g of x is 2x cubed minus 6x. G of x is 2x cubed minus 6x divided by, they say x squared plus 4. X squared plus 4. So this time the degree in the top is bigger than the degree in the bottom. N is 3, m is 2. Whenever the degree in the top is bigger than the degree in the bottom, there are none. So there are none there are no horizontal asymptotes for this function. No horizontal asymptotes for this function. The graph of this one, if that's my x and that's my y-axis, this thing does something like this. There's my function g of x. And C, h of x equals, they give me 8x squared plus 9x minus 5. 8x squared plus 9x minus 5 divided by 2x squared plus 1. 2x squared plus 1. So now, with position number 3, the degree in the top and the degree in the bottom are both 2. So it'll be the ratio of the coefficients, 8 over 2, but 8 over 2 is y equals 4. That'll be my horizontal asymptote. And the graph of this one, and again, take a look at these graphs, this is really important. Y equals 4 would be my horizontal asymptote. Okay, that's y equals 4. And again, these functions can do some really weird things. They can do some really weird things. It'll come up, go over it, and then get close. Remember I told you a horizontal asymptote, a function can cross a horizontal asymptote? Well, it crosses this one. For this function right here, 8x squared plus 9x minus 5 over 2x squared plus 1, my function will cross y equals 4. Okay? And then it'll go up and then start getting closer and closer, never cross it again. It can only cross once. A function may cross a horizontal asymptote, but no more than once. A function will never cross a vertical asymptote. Okay? So pretty straightforward. You just got to have those rules. Okay? You just got to have those rules. Now, how do I figure out? We just said that a function may cross a vertical asymptote. So example 4. So I want to know where does the function cross the horizontal asymptote? I want to know where this thing crosses the horizontal asymptote. And it's the same function. So it's the same function. H of x equals 8x squared plus 9x minus 5 all over 2x squared plus 1. Now we've already decided that y equals 4 is my horizontal asymptote. We've already decided that y equals 4 is my horizontal asymptote. Okay? Well, it's pretty easy. Remember, h of x is the same thing as y. So y equals this thing, y equals 4. Well, if they cross somewhere, then at some point this equation better be equal to 4. So I'm just going to set the equations equal to each other. If they cross, at some point they're going to have the same y coordinate. That point where they cross, that has the same, those 2 points will have the same y coordinate. Okay? So set them equal, and it's still over 2x squared plus 1, sorry. It's this whole function equals that whole function. Sorry about that. Now, how do I get rid of fractions? Well, you multiply both sides by your denominator. If I multiply the left side by 2x squared plus 1, I need to multiply the right side. But over here, they cancel. 4 times 2x squared gives me 8x squared plus 4. 4 times 2x squared is 8x squared. 4 times 1 is 4. And over here, all I got left is 8x squared plus 9x minus 5. Subtract 8x squared from both sides, they go away. Right? And I get 4 equals 9x minus 5. Add 5 to both sides. X equals 1. So they crossed when x equals 1. So the point where they cross, we already knew that y was 4, so they cross at 1, 4. That'll be the point. X coordinate was 1, the y coordinate had to be 4, because the function crossed the horizontal line, y equals 4. So it's never hard to determine where a given function crosses a horizontal asymptote. All you gotta do is set that function equal to that value and then solve, okay? Set that function equal to that value, then solve. So we've got these vertical asymptotes, we've got these horizontal asymptotes. There's one more. It's called a slant asymptote. There's one more type of asymptote. It's called a slant asymptote. So slant asymptote. Slant asymptotes, excuse me, are pretty particular. And let me tell you when a function will have one. A function will have a slant asymptote. A function will have a slant asymptote when the degree of the numerator, the degree of the numerator is exactly one more than the degree of the denominator. So when I have this rational function and the degree of my numerator is one more, exactly one more than the degree of my denominator, that's when I'll have this slant asymptote. Okay, that's when I'll have a slant asymptote. Now, how do I get it? Well, you get it by long division. To find the slant asymptote, use long division. And y equals whatever your quotient is the slant asymptote. And I'm just going to show you one. So to find that slant asymptote, I'm going to use long division. I'm going to divide by denominator into my numerator. And whatever the quotient is, that'll be my slant asymptote. Now remember, when I say quotient, when we do long division, we take a divisor. That's the thing on the outside of that thing. The thing under here is called the dividend. And the thing that you get up here, that's what I mean by the quotient. And you may get a remainder down here, I don't know. Sometimes you'll have a remainder, sometimes you won't. But to do long division, you take a divisor, divide it into a dividend, the result is a quotient plus a remainder maybe. Sometimes some things have remainders, sometimes they don't. Okay. So, let's put all this stuff together. And let's do example 5. They say find the asymptotes. Find the asymptotes, okay? So I want to find the vertical, horizontal, and slant asymptotes. So the function they give me is f of x equals, they give me 2x squared minus 5x. 2x squared minus 5x minus 3 divided by x minus 2. Okay, so let's go ahead and try to factor completely because we've already seen, especially for vertical asymptotes, I have to divide out any common factors if I have them. I have to divide out common factors if I have them. I don't know if I have them or not. 2x squared minus 5x minus 3, 2x and x. The only way to get a 3 is a 3 and a 1. I think it's going to be a 3 and a 1 minus plus. There's my factorization, okay? Well, I clearly see that there are no common factors between that p of x function, 2x squared minus 5x minus 3, and the q of x function in the bottom, x minus 2. There aren't any common factors. So the vertical asymptotes are really easy. The vertical asymptotes will be x equals positive 2, because 2 minus 2 makes a 0 in the bottom. The vertical asymptote will be x equals 2, okay? Well, next is my horizontal asymptotes. Well, the degree of my numerator is bigger than the degree of my denominator. Whenever the degree of the numerator was bigger than the degree of the denominator, then the horizontal asymptotes, there aren't any. So none. Whenever the degree of the numerator is bigger than the degree of the denominator, there will not be any horizontal asymptotes. So all I got left is maybe there's a slant asymptote. And to figure it out, I've got to divide x minus 2 into 2x squared minus 5x minus 3. Okay, long division. Long division, you take leading term divided by leading term. And go to the side if you need to. 2x squared divided by x, that's 2x. And I align like terms. So the 2x goes above the 5x because they're like terms. Now I multiply. 2x times x is 2x squared. 2x times negative 2 is minus 4x. Then I'll subtract that, which really means I just change the signs of both of them and add. So change the sign. That was a positive 2x becomes a negative. This was a negative 4x. Change the sign, it becomes a positive. 2x squared minus 2x squared goes away. Negative 5x plus 4x is negative x. Bring down to negative 3. Divide again, take leading term, negative x, divided by leading term, x. That's negative 1, so minus 1. Multiply, negative 1 times x is negative x. Negative 1 times negative 2 is positive 2. Change the signs and add them. Okay, you get a remainder of negative 5. Well, again, y equals the quotient will be your slant asymptote. So my quotient is this thing up here. So y equals 2x minus 1 is my slant asymptote. Okay, y equals 2x minus 1 would be my slant asymptote. Okay? So they show me a picture of this function in the book. Again, take a look at these graphs, x and y. And I'm going to just do a little bit of it. Okay? Y equals 2x minus 1. Y equals mx plus b, so the b, the y-intercept must be negative 1, so I plot negative 1. Slope is 2 over 1, right? So I go up 2 over 1, back on the line. So there's my slant asymptote. I had a vertical asymptote at x equals 2. So there's that vertical asymptote. And the function will actually do the following. There'll be a piece of the function over here that does that, and a piece of the function over here that does that. So there's a graph of that function. Okay? All right. Well, the next thing we want to try to do, look at our, let's pause. I'm going to pause it.